Welcome to chapter 18. This is the chapter on virtual machines. So, in this chapter, we'll look at an overview, the history of virtual machines, benefits and features, and building blocks. So, we'll look at the different types of operating system virtual machines and their implementations, and also look at different virtualization and OS specific concepts. And then, of course, we will discuss examples. So, one of the key objectives of this chapter is to explore the history of virtual machines, how they came to be, and what are their benefits. Discuss the various prevalent technologies. What are the methods that are used to implement virtualization? And show the most common hardware features that are there to enable virtualization. And then discuss the future, which is discuss the research areas with respect to virtualization. So, what is the fundamental idea? So the fundamental idea over here is that we abstract the hardware of a single computer, of a single machine, and we can basically run multiple operating systems where each operating system thinks that it has a piece of it owns the hardware, right? So each operating system here thinks that it owns the hardware. So, but the hardware is it's a single piece of hardware, right? So how does each operating system that is running think that it owns a specific processor? Well, so this is where the concept of a virtual machine comes in, where a virtual machine is nothing but a virtual processor, which is owned by an operating system. So it appears as if each program that is running on the system, which could also be a full-fledged OS, has its dedicated processor and also other kinds of hardware. So we call this the virtual machine or the VM. And on the VM, we can run operating systems and applications. So a quick idea of the terminology. So the host is the underlying hardware system. The virtual machine manager or the hypervisor, its job is to create and run and manage virtual machines by essentially creating a machine that is identical to the host. So here again, there are some differences in the sense that sometimes we can create a virtual machine which is not exactly identical to the host, right? The native hardware, but we'll discuss that later. And then we'll have a guest. So the guest is a process which is provided with a virtual copy of the host. So basically what happens is that if we have a single hardware, we will run a VMM on top of it, which will create multiple virtual machines. Each virtual machine will run an operating system. And this setup, so in this setup, and on top of the operating system, regular applications will be running. So each application will essentially perceive itself to be running in isolations. It will not perceive the rest of the applications running on other operating systems on the same hardware. So this specific OS is called a guest. So it's a guest OS which is running its own applications. So the key idea is that a single physical machine can run multiple operating systems concurrently. So each having its own virtual machine. So this basically means that if I have a computer, I can run one instance of Windows, one instance of Linux, one instance of Unix. So the cloud kind of environment, if I need, so let's say that I need a Linux environment. So then 10 Linux instances can be provided to me across machines. So a non-virtual machine would look like this. We would have the hardware, the OS kernel, and processes. But in the case of a virtual machine, we'll have the hardware and a virtual machine manager on top of it. And then we will have multiple virtual machines, VM1, 2, and 3, where each one of them would be running their own kernel, and the kernels, of course, could be separate. So as I mentioned, one could be Windows, one could be Linux, and so on. And we will have separate applications or separate processes running on these kernels. So there are different kinds of virtual machine managers and they vary greatly between them. So we have type 0 hypervisors. Type 0 hypervisors are hardware based solutions which essentially provide the entire virtual machine management service via firmware primarily. So firmware is basically these are these specialized chips that are connected along with processors. And in firmware, we manage the hypervisors and the virtual machines. So we IBM LPARS and Oracle LDOM. So these are all virtual machine solutions that essentially work at the hardware level. Then we have type 1 hypervisors, which are, I would say, extremely popular. And so these are extremely popular in an enterprise setup. So there are another class of type 1 hypervisors which are extremely popular in a non-enterprise setup, let's say university setup. But for an enterprise like setup, these are softwares that are built like an operating system. And but it's a very thin layer in the sense they do not provide all the features of a regular operating system. But definitely the features that they provide are enough for virtual machine creation and operation and management. So these include VMware ESX, Giant SmartOS, Citrix Zen Server, and so on. And the other kind of type 1 hypervisors are general purpose operating systems, which also have additional functionality to create and manage virtual machines. So some of these will be Microsoft Windows Server with Hyper-V and Red Hat Linux or even other versions of Linux with KVM. KVM is called kernel virtual machine. So it's pretty much an extension of Linux that allows Linux to also, along with functioning as a normal operating system, to also be able to run other virtual machines. Then we have type 2 hypervisors. So a type 2 hypervisor is basically an application. So the type 2 hypervisor is essentially an application that is running on a standard operating system but is providing VMM features. So VirtualBox, Parallels, even VMware's VM Player, which are essentially regular applications. So these are not operating systems. These are regular applications that I can download and then I can run an operating system on top of that application. So this is the type 2 hypervisors. The type 2 hypervisors, needless to say, are the easiest to run, but they are basically the most, or let's say they are the least in terms of performance. So the most efficient are, of course, the type 0, type 1 hypervisors, and type 2 hypervisors are not that efficient. So there are a few other important notable technologies in this space. The first is para-virtualization. So in general, in virtualization, the kernel of the operating system does not have to be modified. So what this basically means is that the operating system essentially runs as is, and it's simply not aware that it's running on a virtual machine. But in the case of a para-virtualized system, we also modify the kernel of the guest operating system to work in cooperation with the VMM. So this is like a little bit of cheating is there in the sense it is not kind of running as is, but some amount of modification is done. So we are all aware of Java virtual machines and Microsoft .NET virtual machines. So they also provide a virtual environment to a program, but they are not virtualizing a full operating system and runtime, but they are essentially virtualizing a single program. And then, of course, we have emulators. So the most important being the KEMU emulator. So they allow applications written for one kind of hardware environment to run on a very different kind of hardware environment. So let's say they allow applications written on x86 to run on ARM and so on, or vice versa. So the reason this is required is basically because, assume that I have a program which is written for a certain architecture, but then the architecture changes. So I then have another kind of architecture. What do I do in that case? So what is done is that it's a dedicated piece of software that does binary translation. So the Most popular in this space is the KMU emulator, which can be downloaded for free, and it can be run. Then we have application containment, where basically we are not doing any virtualization, but essentially what we are doing is we are isolating the application from other applications. So it appears as if the application is running in isolation. So this makes it way more manageable, and also we can control its interaction with the rest of the operating system. So this would include Oracle Solaris, BSD jails, and so on. So even the new Docker containers would fall in this category, where we provide the abstraction of a file system to Docker. So of course, new variations are coming; they are gradually coming, and we need to watch this space for what are the new technologies that are coming in virtualization. So we look at the history. The first instances of the use of virtualization was in 1972 when it started appearing in IBM mainframes. It allowed multiple users to share a batch oriented system, and then gradually it moved beyond IBM and it moved to other companies. So a VMM essentially provides an environment for programs that is identical to the original machine, the host machine, right? If in the most simplistic way. Naturally, the performance will decrease, right? Because the VMM is in control of the resources, the guest OS is not. Because as we have discussed, we have the hardware, then we have the VMM on top of it. On top of that, we have the guest OS, right? So we can have multiple guest OSs. So let's just draw a single one. And on top of that, we have our applications. So in the late 1990s, Intel CPUs were fast enough, so people tried looking at virtualization. Zen and VMware created technologies that are still used today. So they brought in the era of virtualization. And this ultimately led to the era of cloud computing. So Zen, of course, was para-virtualized in the sense that if we are running Linux on Zen, some modifications have to be done to Linux to run on Zen. Linux will not run as is, but VMware pretty much changed all of that in the sense that we just run Linux on native hardware and it runs. So virtualization, of course, after that has expanded to many OSs, CPUs, VMMs, and so on. So what are the benefits and the features? So the benefit is that the host system is protected from VMs in the sense that VMs can do their work, but given the fact that the interaction of the virtual machines in the host system is this interaction, right, is thoroughly looked at and checked and recorded and monitored, the chances of a virus spreading or affecting the hardware is low. The VMs are mutually protected from each other. And also, the other thing is the sheer ease of running something on the cloud, in the sense, if I have a machine that runs on a given version of Linux, all that I can do is that, and let's say I've developed programs on this machine and I want to run thousands of copies of these programs. All that I need to do is that I basically need to create these virtual machine instances on a cloud, which are running exactly the same version of the OS on which my software was developed, and I can deploy the software. So, in a sense, it allows me to export my custom environment and run it on any machine that has roughly similar hardware. This is not enough. So, this is not it. So, there is much more. So, what I can do is when a virtual machine is running, I can suspend it and I can move it to another machine. So I can have the suspend and resume functionality where I just press a pause button. I take the snapshot of the state, which is of course the program, the registers, the memory, and all of that. And these snapshots can then be transferred to another place and to another machine, and then we can run the virtual machine from there. Or what we can do is that we can take the same program and we can just create multiple clones. In the sense, we can create a copy and then we can run the original as well as the copy. right? So we can create clones. So of course, creating clones is not that important, but definitely freezing, migrating, and suspending is way more important. And the fact is that, let's say that I'm running 1,000 applications on 1,000 servers, and then 50 of these servers, let's say, die or they need to be serviced. Then because I have this functionality of freezing, migrating, freezing, suspending, and then migrating, I can simply, move these operating systems, these VM instances, along with their guest operating systems to other servers. So that is pretty much doable. So this is how I create a cloud. So pretty much virtual machine technology has created this entire cloud computing revolution that we see. Furthermore, it is also easy to deploy custom systems in the sense that modern development is not just restricted to a single software. So it is a single software plus operating system plus much more. So we can create a template, or we can create an environment. And the entire environment can then be migrated to different machines. And so basically we can then run our environment wherever we wish to. And as I've discussed in the previous slide, even live migration, which is essentially pausing a VM, suspending its execution, collecting its state. So we collect a snapshot and then migrating the snapshot to another machine. So naturally, one machine can run multiple VMs. So basically we have an element of migration as well. Migration of the snapshot and then resuming. Right. So all of this can be done. So this is how we have been able to create a massive amount of cloud infrastructure with servers, networking, storage, and so on. And we have been able to create a massive infrastructure where managing guest operating systems, VMs, and so on is very easy. So, what are the building blocks? In general, it's hard to create an exact duplicate of the underlying machine, even though we can get close. So, we are getting better. So, let's look at virtualizing each of the elements of a modern system. So, the first is the CPU. So, most VMMs create and implement virtual CPUs or vCPUs to represent the state of the CPU, and the fact that we are running a program on it, in the sense that, let's say if I have 8 underlying CPUs and let's say there are 2 VMs. So each VM may actually expose 8 CPUs to its guest OS. And in practice, these programs will get multiplexed, but the guest OS will believe that it has 8 CPUs fully under its control. So whenever the guest context is switched onto a CPU by the VMM, all the information or the state information of a virtual CPU is loaded and stored. So, of course, there are many techniques of virtualizing the CPU, as we shall see. But the key idea is that the guest OS always believes that it has complete control of the hardware. And to provide this abstraction, the entire state information of the CPU has to be both saved as well as loaded back when the programs corresponding to this VM are executed. The simplest mode is trap and emulate. So we'll discuss the dual mode CPU where a guest executes in user mode. So recall that there are different kinds of modes. A kernel mode where we can execute privileged instructions. We can interact in IO. We can interact with IO. We can interact with peripherals. And we have a user mode. So in the user mode, what we do is that we do not have the additional privileges of executing certain instructions. So in this case, the guest executes in user mode, the kernel in kernel mode. But the guest kernel, right? The guest kernel, this is important, does not execute in kernel mode, it executes in user modes. So as far as the VM is concerned, it actually needs 2 modes. It needs a virtual user mode and a virtual kernel mode. In principle, this is doable if we can have multiple modes. So modern processors actually have multiple modes and they are known as ring levels, where the ring levels are precisely used for this purpose. But for the sake of this, for the sake of this slide, what we have is that both the virtual user mode and the virtual kernel mode actually run in real user mode. So this is a problem. The reason this is a problem is because the guest OS will execute instructions for which it does not have adequate permission. This will cause issues. So what issues will it cause? Well, there will be certain actions that the guest kernel takes which it is not allowed to. So that will cause a trap in the sense the hardware will raise an exception. The VMM will catch that and it will essentially emulate in the sense it will do whatever the guest OS wanted to do. So this is the key idea. This is the idea of trap and emulate. That the guest kernel tries to do something, the hardware raises an exception, and then the VMM comes into the picture. It takes over and it does whatever the guest kernel wanted to do. So here is the idea in better detail. So the key question is how do we switch from virtual user mode to virtual kernel mode? So we attempt a privileged instruction and this causes a trap, this causes an exception, and this is where the VMM comes in. It analyzes the error, it analyzes what was the operation that the guest OS was trying to do, and then it returns control to the guest in user mode. So this is known as trap and emulate. And in the past, most virtualization products work like this. So what you will see is that the user mode code in the guest used to run quickly, the native speed, but kernel mode code, which means the guest kernel, that was very slow because of the trap and emulate. And especially when you had multiple guest OSs, right? The VMM became a bottleneck because it had to trap and emulate for all. This is why CPUs started adding some degree of hardware support and different CPU modes to improve virtualization performance, which we will see in the subsequent slides. So this is a visualization of the trap and emulate, where we have the guest kernel, user apps, and the VMM. So the guest kernel tries to execute a privileged instruction. It traps. Its action is emulated by the VMM. The VMM updates. And after that, it goes to a vCPU, a virtual CPU, right? So which of course the VMM maintains for every guest OS. And then the VMM basically does whatever the guest OS wanted to do, right, on a vCPU. So it may also modify that, but not significantly though. The original intent is retained. And finally, it returns. As far as the guest OS is concerned, it will not be able to perceive any difference, even though the underlying hard work is being done by the VMM. Another idea or a building block, which is binary translation. So sometimes, right, there is no clean separation between privileged and non-privileged instructions. And sometimes what can happen is that you can have the POP-F instruction, for instance, in Intel. So its job is to load the CPU flags register from, from the stack. Here is the fun part. The fun part is that its behavior varies depending upon the mode that the CPU is in. If it is in privileged mode, all the flags are replaced. If it is in user mode, only some flags are replaced, but not all. But again, the idea is that no trap is generated. Consequently, our trap and emulate will not work. There are other similar problems as well, in the sense that until 1998, the trap and emulate method was considered to be very difficult or near impossible, and the key idea was that this is very hard to do because we have so many of these instructions which have kind of this dual behavior, in the sense that when they are in privileged mode, they have a certain behavior, and when they are in non-privileged mode, they have some other behavior. So binary translation will solve the problem to some extent, in the sense that the basics of binary translation are simple, where we basically take the binary of the whatever application we are running or even of the guest kernel, and we replace it with an equivalent sequence which is more virtualization friendly. So if let's say the guest vCPU is running user mode instructions, there is no issue. But if it is in kernel mode, which means that the guest believes that it is actually in the kernel mode, what the VMM will do is that it will examine the sequence of instructions. I mean, not necessarily every instruction, instruction by instruction, but essentially it will examine a long sequence of instructions by reading ahead. It will look at all of these special or funny instructions. And then what it will do is that it will translate them into a new set of instructions that perform equivalent tasks, but of course, they are more virtualization friendly in the sense that they do not have a varying behavior. What it can instead do is it can make them generate a trap, for instance, and then they will come to the VMM where the VMM can execute the instruction in genuine kernel mode. Or if there are other workarounds, those workarounds can be done. But the key point is that the VMM now has to keep a tab on all the instructions that the guest OS is executing. And wherever it sees instructions that are not virtualization friendly, like popf, these instructions have to be replaced with some virtualization friendly sequence, which can be seamlessly and correctly virtualized. So, towards the beginning of this millennium, mostly translation was being done, where there was code to read native instructions dynamically from the guest OS on demand and generate different binary code, which is roughly similar, but of course with those critical differences that we have talked about. And this process, which also the KEMU virtual machine uses, can be significantly sped up with caching, where we translate the code once the first time we see it, where once being the operative word. And whenever the guest executes code containing the special instruction, instead of the instruction, the cache translation for that sequence is used. So something as large as Windows XP with 950,000 translations at 3 microseconds each, the total amount of slowdown was limited to around 5% over native. The reason being that we very selectively choose the parts of the execution that are going to be translated. And also the translations themselves are quite optimal or optimized. And we translate once and we keep it in a cache. So we don't translate it all the time. We simply read the translated sequence from a software cache. Well, it's not the L1, L2 kind of cache, but it's a software cache, a cache for storing translated sequences. So in this case, our workflow will be slightly different. We'll have a user process. The VMM will be reading instructions. The moment it encounters a special instruction, in a sense, it sees that, it replaces the code of the guest OS with a translated sequence. And then that translated sequence works on the vCPU and the rest remains the same. Another important issue, other than, of course, virtualizing the CPU, is the issue of virtualizing the memory. And in memory, what happens is that again, the guest OS thinks it is in complete control of the memory, which it is not. Right? So virtual memory, of course, varies for every process, but the physical memory is one for the entire machine. In this case, that's not the case because the physical memory is still one, but each virtual machine needs to provide the illusion that the physical memories are different. So the question is, how can the VMM keep a page table state for both guests believing they control the page tables, right? Assuming that there are two guests. So one common method, which is primarily used in trap and emulate and binary translation, is known as a nested page table, NPT. So each guest maintains a page table to translate from virtual to physical addresses, right? So this is a standard page table that a guest will maintain because a guest doesn't know that it's being virtualized. But here is the fun part. This is what the VMM does. The VMM maintains per guest, for each guest, it maintains NPTs to represent the guest's page table state. So similar to the fact that a vCPU stores the CPU state of the guest, so in this case, the nested page tables essentially represent or store the guest's page table state. Let me explain this in another way. So it is actually a two-level mapping that we are looking at. So from the guest, we have the virtual address to the guest physical address. And from the guest physical address, we need to go to the host physical address. So the guest OS's page table will store the mapping between the virtual address and the guest physical address. The mapping between the guest physical address and the host physical address is again stored in another set of page tables. These are known as the nested page tables. So this basically means that whenever we have a TLB miss, what the VMM needs to do is that it actually needs to do a double translation, in the sense it needs to translate from the virtual address of the guest to the physical address space of the guest, and then from there to the actual physical address. So this in a sense causes well, not only because of more accesses, it may cause more TLB misses, but it definitely makes a TLB miss more expensive, and that leads to slower performance. So maybe I'll just discuss the next slide over here, and then I'll come back to the previous one. So what I was basically referring to is that the guest process generates addresses using the guest physical address, sorry, the guest virtual address. And subsequently, if there is a TLB miss, then there is a page fault. So the page fault is traditionally handled by the page fault handler of the OS. So in this case, the guest OS is sent the virtual address, so it updates its paging and data structures. And it assumes, because it doesn't know that it is running on a hypervisor, it assumes that it is running on raw and native hardware. So what it basically does is it internally creates a mapping between the guest physical address and the guest virtual address. But what happens is that this mapping has to be additionally translated, right? It has to be translated after this from the guest physical address space to the host physical address space. So this is where we need another data structure, which is known as a nested page table, which provides the additional level of translation. And the way that a page table translates, we have already seen this threadbare in previous chapters. So what we basically do is we do the translation, and since we are looking at slightly longer addresses, we are looking at 64-bit addresses. So in this case, instead of having a two level with a primary and a secondary, right, and then the offset, three levels actually. So in this case, we'll have five levels where the top bits will point to a top level, then one more level, then one more, then one more, and then one more, right? And so basically, so it follows the same sequence as the normal page table access, but the normal page table access that we showed in a previous chapter was only 32 bits, and given it is 64. So what we basically do over here is that we use many more levels, right? And after that, we get the final host physical address. So this is what is stored in the nested page table of the hypervisor. So coming back, this was again a software structure primarily. But modern hardware have also added some support for both CPU virtualization as well as memory virtualization. So if you think about it, all kinds of virtualization other than para-virtualization, which is basically where the operating system is aware that it is running on a hypervisor, it needs some kind of hardware support, howsoever little it is, but it does need some hardware support. So more support will ensure that the hypervisor is more feature rich, it is stabler, and it also provides better performance for a large number of heterogeneous guests. So Intel added VTX instructions in 2005, and AMD added the AMD V instructions in 2006. So CPUs with these instructions do not require any binary translation, do not require para-virtualization. So what they do is that they define two CPU modes known as the guest and the host. So in this case, the guest basically means it's the guest operating system and the host means it's the host or the hypervisor. So of course we could have multiple ring levels which are also known as privilege levels. So the key point over here is we could define one kind of privilege for the guest application, one for the guest OS, and then the hypervisor and so on. So this is something that modern processors have. So the VMM, the hypervisor basically, can enable the host mode to define the characteristics of each guest VMs and switch between the guest VMs, right, for overall management. In the guest mode, the guest OS will think that it is running natively. It will see devices as the VMM has allowed for this particular guest OS. So what happens is hardware provides some support for virtualizing the devices, and whenever any privileged instruction is issued, if it cannot be handled by the guest OS, so of course which instruction to handle in the hypervisor and which the guest OS can handle, this of course the hardware can decide. But in general, we have looked at the issue of privileged instructions in the past where depending upon the mode they behave differently, but of course modern hardware is trying to remove that. Then of course we can have a much better split. So whenever there is a privileged instruction, there is a trap to the VMM. Furthermore, instead of using software to maintain the context of a virtual CPU, a CPU with these advanced hypervisor features can maintain the state for virtual CPUs. So context switches as such are not needed, because the point is that we can store the entire state. So you do not actually have to store and reload the state, but you can just say that look, just reload state number 5, which will be done automatically. Also, there is some hardware support for nested page tables as we just saw. So nested page tables basically means it's a multi-level access. Any TLB miss will become expensive in the sense multiple page tables have to be consulted. And of course, other interactions with the hardware like DMA and interrupts, they also, it becomes much easier to support them primarily because there is some amount of hardware support which essentially ensures that interrupts, for instance, are delivered to the correct guest OS. All DMA events are delivered to the correct guest OS that initiated the operation. So this bookkeeping is done. Alright, so now let's look at the types of virtual machines and implementations. So of course there are many variations, many kinds of virtual machines. We don't have one kind. So as we have seen, the primary tasks of virtual machines are CPU virtualization and memory virtualization. So CPU virtualization was primarily to deal with the privileged instructions, and memory virtualization was primarily to deal with virtual memory. So we did discuss nested page tables over here, but there is something called shadow page tables. So in shadow page tables, what happens is that we actually maintain more information, right? So we don't go through a two-level access. As you can see, this is two-level, right? In the sense we first do one conversion over here and then we do one more conversion over here. But the reason for this is that the VMM is not aware of the processes that the guest is running. If let's say this information is made available, we could have a shadow page table. So for the shadow page table, what will happen is that we can directly do a translation from the guest virtual address to the host physical address. So this is directly possible to do, but of course one negative side effect of this is that the virtual address you need to understand is process specific. So it is not specific to an OS, it is specific to a process. So let us assume that there are n processes. So of course we need a page table for each one of them. And in this case, we just needed one extra page table, which was to just translate from guest physical to host physical. But in the case of a shadow page table, what we actually need to do is that the guest OS will have its n page tables, but we'll also have n shadow page tables which will have a mapping between the guest virtual address and the host physical address. So we'll be using more storage, we'll have more state and more bookkeeping, but a TLB miss will become less expensive. So the key point that you need to understand over here, the classic nested page table versus shadow page table business, is that there is a trade-off between storage space and performance. So now coming back to our discussion, there are many variations of VMMs. So every virtual machine will have a life cycle where it will be created, resource will be assigned to it, resources like the number of cores, memory, networking details, storage, and so on. For a type 0 hypervisor, of course, which is running on firmware, resources are usually dedicated. But other types, what they will do is that they will create multiple VMs and they may dynamically either partition the resources or share the resources. Right? So there are two options. Either we can have a hard partition. In the sense you take 10 cores, you take 8 cores, or we can share. When a resource is no longer needed, the virtual machine can be deleted, which will free up resources. So these steps are simpler and faster than with installing things on a physical machine. All of us have installed operating systems on programs like VM Player or VirtualBox, so we know how easy it is. And we also know how easy it is to migrate a VM from one machine to other, suspend, resume. All of that can be done very easily. Of course, we can have virtual machines sprawl in the sense in a cloud kind of environment. We can have tons of VMs and some may be active, some may be inactive. But the good news is that these VMs can also be persisted to disk, and later on, if the user is interested, they can be brought back and made alive. So a type 0 hypervisor, as we have looked at, is an old idea. So this is probably the oldest in its in its class. So they are also called partitions and domains, and this is a hardware feature which is implemented in firmware. And the OS will run as is, but it is just that all the management of the virtual machine is done in firmware. Not a lot of features are provided, and it is also hard to add new features primarily because we are not relying on a software layer, but we have a firmware layer. IO is a challenge. It is difficult to have a lot of devices or controllers for each guest. Occasionally, a hypervisor may implement a partition where a control partition where you can have either daemon programs or guest programs which can communicate with for shared IO, right? So occasionally this abstraction that the OS is not aware is broken occasionally. So you may directly want to communicate with hardware, and this is sometimes needed in type 0 hypervisors, but this is clearly not something that is desirable. But one advantage of course is that we can run a type 1 hypervisor on top of this, in the sense that we can run virtualization within virtualization, which means a guest itself can be a VMM for other kinds of guests. This is a visual description of a type 0 hypervisor. So as you can see, we have the hypervisor implemented in firmware. This is in parallel with the IO devices. Then of course we have the CPUs and memory. They sit on top of this because the firmware is the lowest level. And then we can support a lot of guest operating systems. So the guest operating systems, so furthermore, we can have virtualization within virtualization over here, as is mentioned over here. So in a guest, we can support multiple guests. So that also is possible. So this shows the flexibility of the type 0 hypervisor. Then of course we have type 1 hypervisors, which in a sense are becoming the standard. They are becoming data center operating systems. So in data centers, what happens is we have a large number of machines. So we have, so the moment that such a system is on the cloud, Somebody may want, 10 Linux machines and 10 Windows machines and so on. So it is always best to have a type 1 hypervisor which sits, uh, which is pretty much like an OS. So the type 1 hypervisor is pretty much like an OS, but a very basic OS, of course, which provides some basic functionalities. On top of that, we can have individual virtual machines. So this allows for server consolidation in the sense that one server can be used to host multiple OSs, multiple environments, and so we use much less hardware. And furthermore, we have already discussed moving guests between systems to balance performance. So where we can take a snapshot of a running VM and migrate. So this part has already been discussed. So in type 1 hypervisors, so what we have discussed is that it is more or less like a thin operating system, but it is a special purpose operating system. So it does not provide a system call interface for running regular programs. Instead, it provides special calls to basically create, run, and manage guest OSs. And the type 1 hypervisor can run on a type 0 hypervisor, but it cannot run on other type 1 hypervisors. But it can run on a type 0 hypervisor, so it can provide virtualization within virtualization. And needless to say, when a type 1 hypervisor runs, it runs in kernel mode. So guest operating systems are never aware that they are running on a virtual machine. And needless to say, the type 1 hypervisor over here has to implement device drivers to interact with the underlying hardware. So if this is the underlying hardware and the type 1 hypervisor is over here, so then within this we need special device drivers to interact with the hardware. And naturally, on top of that, whenever any virtual machine which is running a guest OS, when that tries to interact with the hardware, the job is to intercept that call and make it pass through the device driver of this. So the device driver basically does the job of translation, of course, in the sense that some device may be shown to the virtual machine, which may not be the actual device. So it does the job of translation, as well as if there are multiple requests from multiple virtual machines, it provides the illusion that these are actually separate devices. So internally it implements queuing and so on. So along with that, the type 1 hypervisor, along with virtualizing IO, it provides regular services such as virtualizing the CPU and memory management. So another variation of this is that we add more features to the type 1 hypervisor. So we make it more like a general purpose OS that also has some VMM functionality. So Red Hat Enterprise Linux with KVM. KVM is kernel virtual machine. This is very common. Windows again with Hyper-V, Oracle Solaris. So these are some of the examples where the hypervisor layer has more features. So it performs its normal duties as an OS as well as it has VMM duties. And such OS based solutions, Linux KVM being the most popular, typically do not have that many features and are typically not that efficient as dedicated type 1 hypervisors. But they are still very popular because a regular OS can do all the job. So in many ways, what happens in such kind of augmented type 1 hypervisors is that it treats guest OSs as just a separate process that is running. Of course, it is handled in a special way, particularly with regards to special instructions and memory as we have seen. But the abstraction is that the guest OS is a process. So now we come to type 2 hypervisors, which are one level above. These are not very interesting from an OS perspective because this is like a real regular process, and on top of that an OS runs. So there is very simply very little OS involvement per se. The virtual machine monitored over here, or the virtual machine manager, whatever you may choose to call, is just simply a process which is run and managed by the host. And the host need not know that there are VMMs which are running their guests. But this clearly has the poorest or the lowest performance out of all because first it doesn't take advantage of both hardware features as well as software features. But a real benefit is that this can be used by students in the sense that they can download VirtualBox and let's say that they have a Windows machine but they have been given an assignment on Linux, then they can run it as a regular process on the native host and then they can run an OS on top of it and then they can do their assignment. So clearly in terms of performance, it's not great. It is the slowest of all three. But in terms of ease of use, it is needless to say the best. Now we come to para-virtualizations. In para-virtualization, the code of the OS has to be changed. It has to be modified. So it does not fit the classic definition of virtualization because in a classic definition of virtualization, the OS is not aware that it is running in a virtual mode. But in this case, the OS has to be aware that it is running in a virtual mode. So in a sense, we are not actually seeing the hardware getting abstracted or virtualized, but it's still useful. It's useful in the sense, so this is the earliest technology, it came the first, right? And then of course in a non-para virtualized operating systems came after that. But with some OS support, so basically in this case what happens is we have the guest OS and then we have the host OS. So normally speaking, the guest OS should not be aware that it is running in a virtualized mode. In this case, it is aware, and given that it is aware, it is possible to establish a very efficient and effective communication channel between the guest and host OS, and this is why this can be made quite efficient. So as a result, many a time when we are just looking for performance and we want to let go of the other gains, we may want to use a para-virtualized solution. And this, I mean, as I said, this was the earliest idea. It's not extremely popular as of today. And as the hardware support for supporting virtualization has grown, this is not needed. This is less needed. Zen is the leader in the para-virtualized space, whereas Zen is like a special kind of Linux where the guest OS can be made aware that it is running on a VM. But one advantage is that if we just look at Zen, Zen did have some advantages. They were reasonably revolutionary for its time, which was it had very efficient IO. In the sense there was a very efficient communication between the guest and the host. And so the host in this case is the VMM. So the way that this was done is that the device, so the host basically and the guest, they shared a circular buffer. And so then the circular buffer is nothing but a circular array, something like this. And we had one circular buffer for every hardware device or every IO device. And so what used to happen is that this was used for bidirectional communication of data. For every data was converted, for every datum was converted to a packet and it was stored in the circular buffer. And it was, so this was the main data structure, which is quite efficient to transfer data between the guest OS and the host OS. So the way that the circular buffer worked is like this. So this is a visual description of the circular queue. So in the circular queue, of course, this is just a circular queue of buffers. And this can also be implemented with a simple array. So that's not very difficult, but regardless of how it is implemented, let us look at the core idea. The core idea over here is that we have a bidirectional communication between the guest OS and the Zen hypervisor. So the Zen hypervisor receives requests from the guest OS and it sends responses back to the guest OS. So they establish a queue among them where there is a single producer and a single consumer. So what you see over here is that the direction of production is like this. So as the guest OS produces new requests, it just moves in this way. And as Zen consumes the request, it moves in this way. So in a sense, the pointers, the production pointer and the consumption pointer are never read or written by different entities. So the consumer always consumes, it modifies its consumption pointer, and the producer always increases the production pointer. So it is possible to prove that in a single producer consumer scenario, this actually becomes what is known as a weight free queue. So this is a fairly deep result, but it's a good idea to just remember this term a weight free queue. So what this basically means is that there is no need for explicit synchronization or waiting or locking or anything like that. In fact, you can also prove that every request will get satisfied within a bounded number of internal steps. So this is quite a deep result, but the key idea that should be kind of imbibed over here is that we have a single producer, single consumer scenario, which in concurrency theory is highly desirable. So for the reverse path, again we have a response producer, which is Zen, and we have a response consumer, which is the guest OS. So the job of the guest OS is to consume responses. It will again move this way, consuming responses, and the response producer will be producing responses. So it will basically take these free blocks and add a response to it. So needless to say, both the queues cannot overlap. So a check is required to ensure that they don't overlap. But an advantage of having such a circular queue is that you are not pre-allocating resources to any one kind. So if let's say we have a lot of requests and very few responses, this can very flexibly handle that situation. And also the reverse situation where you have few requests, but the responses require a lot of buffers. So then also that situation can be handled quite easily. So this in itself is quite a flexible structure. So needless to say, flexibility is one advantage. But the key advantage is that the requirements for synchronization and concurrency are not there, if of course the code is written in a certain way. And the theoretical term is it's a weight-free queue. The exact implications of this will not be clear to you at the moment unless you understand that aspect of concurrency theory. But the key point is that such queues are highly desirable, and that is why the designers of Zen have chosen this. So Zen, needless to say, is a leader in the para-virtualized space in the sense it was the first such product and it continued its dominance for some time. So memory management does not include the nested page table design that we have seen earlier. So each guest has its own read-only table. So it is not that the host tries to catch the calls to modify the guest page table and so on. So that is not done. But the guest uses something called a hypercall. So hypercall is basically an interface, something similar to a system call, where the guest can call the hypervisor. And whenever any page table changes are needed, the guest directly informs the hypervisor about a change in the page table without going through a complicated route of the host basically monitoring the accesses of the guest by marking some pages as read only, and when we try to access that page there is a fault. So that is kind of a longer process, but given the fact that we are para virtualizing and we are modifying the guest, the hypercall mechanism should be supported such that we can gain more performance. Another advantage is that if we have those older x86 CPUs, an example that we had seen, that the same instruction behaves differently in privileged and non-privileged mode, it's quite easy to take care of such issues with para-virtualization. And, you know, any other idiosyncrasy that is there of this kind, para-virtualization can also take care. But of course, it does increase the overhead of the OS writers, and then now it also increases the coupling between the VMM and the guest OS, which in other cases is not there. But if we look at modern CPUs and all their extensive hardware support, Zen no longer requires guest modification in the sense Zen has also matured and it has gone out of the para-virtualized mode. So para-virtualization is an old technology. It's not going to survive in the future because having the guest OS and the VMM independent is something that is highly desired these days, and it's also the market standard. So now coming to, if you will, you can call it a type 3 hypervisor, which is basically virtualizing the programming environment. So this is not classical virtualization, but it uses similar techniques. Where a programming language is built to run on a custom virtualized environment, the way Java is designed, for instance. So Oracle Java has many features that require it or that depend on running it on a Java virtual machine, which is a very simple machine that is a stack-based machine. And what virtualization in this case basically means is that we are providing a set of APIs to a language to make it more expressive and to give it certain features. And any program will use those APIs, and at runtime, we'll have just-in-time compilation, where basically the APIs will be compiled to the native platform, the host platform. And another advantage of the JVM system is that we have our source code, the .java file. The .java file is converted to bytecode, which is a .class file. So the .class file is bytecode, and this assumes a virtual machine, a stack-based machine, as I discussed. And the stack-based machine is a very generic machine. So, I mean, it's also a virtual machine. So, but at runtime, the class file is actually converted into executable code depending upon where you are running it. So this actually gives Java the platform independence. And then, of course, at runtime, we have a very efficient JIT compiler, a just-in-time compiler, which converts the class file to machine code. So one thing you will observe that a Java program gradually gets faster as you run, and the reason is that the system actually learns. It profiles the running program and it learns its execution pattern, and based on that, it creates more and more efficient machine code. So what are the different types of VMs? So the different types of VMs that we would look at here, what we will consider is that we have looked at traditional virtual machines. So in a traditional virtual machine, the idea is that we run a guest OS with or without modifications, that doesn't matter, on a underlying host system. Then of course we looked at programming language VMs, which we can consider as type 3 hypervisors, where a programming language is compiled with a virtual machine in mind, and at runtime we have a just-in-time compilation. So here we are looking at something different. So what we are looking at is emulation. So classically what we have is that we assume that the underlying CPU, at least the same CPU, the CPU family is the same. For instance, if the guest OS is compiled in the x86 assembly language, then the CPUs that we are using it to run are also x86. That is our assumption. But the key point over here is that what if we want to run x86 code on, let's say, an ARM machine? So in that case, we can't use virtualization, but what we will instead use is we'll use emulation. So what emulation does is that it translates all the guest instructions to the host instruction runtime, at runtime dynamically. So one advantage is that, look, if we have old outdated servers which use a different variant of the instruction set or a different instruction set, and if you have newer program compiled in a different instruction set, one will run on the other. No problems with that. But the main issue is we can't do it instruction by instruction because that will become too slow. So what happens is, I'm talking about the KEMU project, which is by far the most popular emulator project as of now. So what that does is it considers a block of instructions. Then it translates the entire block and it caches this. So the next time we come to this block, we don't have to retranslate it. We can just use the cached set of instructions. So with this, what happens is that the performance overheads reduce substantially. And of course, modern avatars of KEMU also do this in a parallel thread. But the key point is that this process of translation and caching and translating a full block and caching it is what gives KEMU its speed. So as of today, For some applications, particularly when there is no choice, emulation is not that bad an option. And this is getting more and more popular in the sense whenever we have newer machines, particularly when certain instructions are not supported. So the instruction set broadly may be the same, but you may still have some instructions that are not supported. So a solution like this will work. And the other is that in the world of gaming, where you have a lot of old legacy games which are running on old consoles which are obsolete now. But given the fact that we have a lot of people who used to play those games and they are kind of emotionally attached to them, what we can do is we can emulate the old gaming consoles on newer gaming consoles, and that would give us, a charm of the old world. So the emulators are used over here as well. So now we have discussed a fair amount of virtualization, different kinds of virtualization, memory virtualization, IO virtualization, CPU virtualization, and so on. So our next target is we'll look more at application containers and zones in the second video of this series, right? So basically for chapter 18, the first video ends over here. In the second video, we'll start from here, slide number 35.